Hey, ladies and gentlemen. 8.3 is entitled Center of Mass, Equilibrium, and Rotating Frames of Reference. We have talked about center of mass before. The center of mass of an object is just the point where we consider gravity to be acting. And we've talked about it with a human being. The center of mass of a human being is their belly button. And if you track the center of mass, it will take that parabolic trajectory. But center of mass also affects stability. For instance, in this first picture I have here, there's a tennis racket, and if you take that, as long as your center of mass is above your base, you're stable. And so putting your center of mass, and if you were to stand your tennis racket straight up in the air, it would be stable. If it's not, what happens is you create a torque. As this center of mass is pushing down, it actually, if this would be considered your pivot, and what it does is it's actually cranking this around, which turns this thing and makes it fall over. You've maybe heard center of mass or stability when it comes to cars, or even like a box. Like if you push on a box to tip it over, maybe you've had a box in the back of a car and you go around a corner quick enough and you get the box tips over. This force right here, if you were to do that, this would be the centripetal force right here. Going around the corner, and then you've got a pivot here, and you've got two competing forces, two competing torques. You've got gravity wanting to crank it this way, and then you've got this centripetal force, or this force that's pulling it this way, competing with it this way, and depending upon who wins, that dictates stability. Once you get it to this point right here, if gravity is directly above this, now this is going to win. And once this gets past the base right here, this being the pivot, now they're both working against to tip this box, and this box is going over. Cars, the same way. You've heard maybe things say that it's got a very high center of mass. A van, for instance, has a very high center of mass, this distance right here. You go around a corner, and as long as this is above the base, you're good to go. And imagine if this was a higher center of mass, then you'd be tipping over. So how center of mass affects stability? As long as your center of mass is above your base, you are good to go as far as stability is concerned. Equilibrium, that's part 2 of 3. Equilibrium deals with things at rest. Equilibrium, we mentioned before. Equilibrium, there are 3 specific things. 1, all forces cancel or equal. Meaning that if I were to add up all the forces that go down, they have to equal all the forces that pull up. Sometimes I'll write this as the sum of all forces in the y direction have to be equal to 0. The next thing that's true is if you add up all the forces that pull to the left, they have to add up all the forces that are pulling to the right. And sometimes I'll write it like this, that the sum of all forces in the x direction have to be equal to 0. And then lastly, maybe I want to erase this one here. All torques cancel equal. So that 3, if you add up all the torques that are clockwise, they have to equal adding up all the torques that are counterclockwise. Sometimes you'll see that the sum of all torques equal 0. So that's what equilibrium means. Everything pulling down has to equal everything up, everything right has to equal everything left, and every clockwise moment has to equal every counterclockwise moment. And here's an example of this. You've got a ladder. It's 1.8 meters long. It's resting on 2 sawhorses. Sawhorse A is 0.6 meters from one end. So this whole thing is 1.80 meters long. So halfway is 0.9. So one of these sawhorses is really close to the center. we'll call it sawhorse A, and it's 0.6 meters from one side. Sawhorse B is 0.15. So these two together are 0.75, so maybe I'm just going to label this distance right here because maybe it will come in handy. I don't know. I like to label all these distances. That's going to be 1.05 meters. All right. What force does each sawhorse exert on the ladder? So what's going on here is there's a force right here at A, an upward force provided by ladder A. There's an upward force at ladder B, and at the very center, there's gravity. This is the force of gravity. Earth is pulling down on the ladder. And you know what? I think what I'm going to do is just to draw this a little bit better, I'm going to go like this. Because A and B have to be equal to gravity. That's just a truth of equilibrium. And that's kind of what we wrote before, that everything down has to equal everything up. So that's actually, I have two unknowns. So the way we're going to solve problems like this is we have to come up with two equations. So steps. Draw a picture. Step 2. With an equilibrium problem, you have to develop as many equations as there are unknowns. In my case, I've got two unknowns. Develop two equations using all these things. So what I'm going to do, first of all, I'll take the very first one that I did, that everything pulling down has to equal everything pulling up. I'm using a lot of big words here, but really what I'm saying is that the force of gravity on the ladder is equal to FA plus FB. And I should know the force of gravity on the ladder. I think it says it's 5.8 kilograms. So if I take 5.8 and then I multiply by 9.8, I should be able to get the force of gravity. 57 newtons. So down here, here's one equation. 57 equals force of A plus the force of B. Simple as that. There's equation number 1. Equation number 2. I'm going to use a torque. So I made my first equation, everything down equals everything up, and number 2, I'm going to use the torques. So I'm going to put a pivot someplace, and it doesn't matter where you put your pivot. I'm just going to put one somewhere, and I would recommend that when you do this, put your pivot at an unknown force, and I'll show you why. When you put your pivot at an unknown force, this force right here is cranking this counterclockwise, and this force right here is cranking it clockwise. These two torques have to equal each other. This force right here is not exerting a torque because it's like pushing on the hinge. So the torque from the gravity and torque from force B are going to equal each other. So add up all the torques that are clockwise, and they have to equal all the torques that are counterclockwise. Maybe I'll get this down out of the way. So this one's a counterclockwise torque. So I take the force, which is 57, and notice I put it on the right-hand side, times the distance. Oh man, I got to find this distance right here. So maybe I have to do a little bit more thinking. This whole thing is 1.8, so the middle is 0.9. And so this, if this distance right here is 0.9, this is 0.6, so this has to be 0.3. So the distance away from my pivot is 0.30. And now I've got a clockwise torque. It's the force at B times its distance away from the pivot. That's 1.05. So now I can solve it. So I'm going to solve this for a force at B. I take 57 times 0.3, and then I divide by 1.05, and so I get 16. So the force at B is 16 newtons. And then I'm going to take this and I'll put it back into my other equation, and I can find the force at A. So 57 equals my force at A plus my force at B, which is 16 newtons. So my force at A is just 57 minus 16, which is 41 newtons. And it should make sense that A bears the brunt because it's more towards the middle, and B doesn't have a lot of force on it, it's over towards the end. So that's how we solve problems that involve equilibrium. You've got a couple unknowns, two unknowns, so you have to come up with two equations to do that. The last thing I wanted to talk about today that your book makes mention of is the Coriolis effect. The Coriolis effect is a weird phenomenon that happens when you're on something that spins. So I have a couple videos to show you just to give you an idea of what the Coriolis force is.
To an observer above the merry-go-round.
So these are kids on a merry-go-round, and what they're doing is they're just rolling a ball back and forth. From this above view, see how the ball goes straight?
Sitting on it, the ball appears to curve to the left. This exemplifies the Coriolis force.
So if you were actually on the merry-go-round and you're going fast enough, you throw the ball and then you turn and then you can catch the ball. Like you can throw and catch the ball to yourself, which is what this girl actually did right here towards the end.
This exemplifies the Coriolis force.
The ball comes right around back to her.
Whereby, to an observer on the rotating Earth, the path of an object appears to be deflected, and this is a result of the Earth's rotation.
And there's another example of this. It was more of an animation.
An object in motion appears to be deflected from its course, as if a force is pulling it sideways. To demonstrate this point, let's imagine a game of catch being played by two people on a merry-go-round that spins like the Earth but is flat. Without rotation, the ball appears to follow a straight path from thrower to catcher. Imagine the ball is tossed from the center to someone at the edge. With rotation, the ball still travels in a straight line in space, but because the catcher is moving, the ball misses. From the vantage point of the catcher, the ball appears to curve away. The direction of apparent motion is to the right when following the path of the ball. Now the ball is thrown the other way. Because the thrower is moving, the ball has a velocity component to the right. The motion of the ball appears deflected to the right, and the ball misses the catcher again. Let's look at a throw across the merry-go-round. Both people move with the merry-go-round. The ball is thrown. Although it flies straight, it appears to be deflected from its original path. Apparent deflection increases as the ball travels farther. In the southern hemisphere, rotation is clockwise when viewed from over the pole. Again, the ball follows a straight course, but its apparent flight path is diverted. This time, the effect is to divert the motion to the left. On Earth, all free-moving objects, including masses of air, are subject to the Coriolis effect. In the northern hemisphere, objects are diverted to the right, as viewed from the direction of original movement.
And this is why storms, hurricanes always spin in that direction.
To the left.
And we call typhoons in the southern hemisphere, they spin counterclockwise. So that kind of is just an example of the Coriolis effect. Trying to throw something is unattached, it's above a rotating frame of reference. Well, that's what we have. That's that is 8.3. Deals with center of mass and how it relates to stability. As long as your center of mass is over your base, you have stability. Equilibrium, there's 3 things when you have equilibrium. All the down forces equal the up forces, left forces equal the right forces, and then clockwise torques equal the counterclockwise torques. And then lastly, the Coriolis effect. The Coriolis effect is just an apparent motion. It's really traveling in a straight line. This yellow line right here, this represents if you threw a ball, all objects move in a straight line. They do, but your frame of reference, you're looking at it from a rotating frame of reference, so from your point of view, it looks like it's curving, but really it's not.